Good morning, good afternoon, good evening to everybody. My thanks to Denise and the organizers of this wonderful conference. And I'm really happy to connect with all these wonderful female colleagues at this event. And I look forward to the future get-togethers. And so I wanted to start my talk with giving some background on myself. And I would say that the whole talk of this background could be, theoretical physics to quantum computing applications. So now, why did I go through a few slides here? So I was born in Indianapolis, Indiana. And then the first big change and opportunity I had is I went to Harvard in Cambridge, Massachusetts, and I was a physics major. Then after I finished at Harvard, I was in Cambridge in the UK for 1 year to do part 3 maths as a Churchill Scholar. And I got a master's in applied maths there. And then I went on to do my PhD at Cornell. And while I was at Cornell, and also at undergraduate, I spent summers working at Bell Labs. And so each summer at Bell Labs, I thought, I met more and more people, more and more colleagues. I had so many friends on the East Coast, and I thought my life was more or less all just set. And I thought, this is great. I'm going to be living in Murray Hill, New Jersey, which is actually a very nice part of New Jersey. It's in trees and, and then I did a postdoc at Harvard in high temperature superconductors. And as I said, and while I was doing my postdoc, IBM came calling. And they asked me to come interview. And so I thought, oh, California, San Jose, who do I know there? And so I thought, well, why not interview? And so I went out there, and then at the end of the interview, I was talking to a senior manager there, and he said, I see you've worked at Bell Labs a lot. And I said, yes, and I have a lot of friends on the East Coast. Bell Labs is a great place to be. At that time, it was a great place to be. Now, of course, it's a very, very different place. And then he asked me an interesting question, which I have up there. He said, what would you rather work on, telephones or computers? And I realized I knew the answer to that. I'd rather work on computers. And so decision I made, moved to California, started IBM research, and I liked it. And I found, I like change and opportunity. And that's, in fact, a good summary of, my career. I like change and opportunity. So 5 years after starting at IBM, I became a manager. I got married. We bought a house, started fixing it up. 3 years after that, had a son, and my management duties grew, 20 people in my group and more. I was managing a group of experimentalists, exciting research on giant magnesis read heads, which at that time were cutting edge research, and these days are found in all magnetic hard drives. Worked on magnetic media. I would go down to the plant site and talk to the manufacturing people. It was an interesting life. And I found, what did I find from this? I found that applied topics are as interesting, engaging, and satisfying scientifically as fundamental topics can be. I found a large company is an excellent place to find a diversity of important areas that find applications. And I found that working in these big teams, I like collaborations much, much better than working alone. And then after I worked on that, I switched to a satisfying career doing theory for the scanning tunneling microscope group at IBM. This is the group that worked IBM with atoms. And it was very exciting fundamental research. I did so-called HPC, high-performance computing projects to model every electron from magnetic atoms on the surfaces. And I did that for a while. And as I said, I don't like doing the same thing for long periods of time and science. So when quantum computing came up, the chance to work with great new colleagues, some of whom I'd known for a long time, but never worked with before, and others who great new hires. And wonderful aspects about quantum computing at IBM is essentially one big research family, and you meet people in several labs, collaborate with them, and collaborate across research groups. And I joined IBM Quantum. So IBM Quantum So IBM does quantum with superconducting qubits, and I'm the first talk of this conference, so I'm going to do a little bit of an introduction to quantum computing. So somebody's saying do a full screen. I think that's a good idea. Let's do here. How is this, everybody? Now I can't see the chat, so let's assume that this is okay. I hope this is better for people. Somebody was saying share your screens, do the whole full screen. I hope this is good. So IBM Quantum. So IBM is it has not just the research lab at Almaden. It has one all over the world, and quantum computing is done in a lot of these places. And what is the power of quantum computing? Well, with classical computers, the potential power of a classical computer doubles every time you double the number of transistors. And this is an IBM Power 9. In fact, that's a type of computer I work on when I do my HPC calculations. And on the right, we see a 16-qubit device, and here the potential power of a quantum computer doubles every time you add one additional qubit. How do quantum computers work? Well, universal quantum computers have two aspects that are very important. There's superposition, and then there's entanglement. Superposition says that a qubit, a single qubit, can exist in a number of different states where we can actually model the states it can take on the surface of a sphere. So not just 0 and 1, but every state on the surface of the sphere. And entanglement, where the states of entangled qubits cannot be described independently of each other. And so when you have two qubits that are entangled, if you change one, it definitely changes the state of the other. And if you measure one, you end up either collapsing or measuring the both. So now let's see. Quantum computing has different aspects. And quantum computing, it has a stack, as it were, and you can work on algorithms. And I'm going to be talking a lot about that because that is where I work. Or you can work in hardware. And I just wanted to show this one slide on the hardware, where the qubit for a superconducting quantum computer is composed of something called a Josephson junction, two of them, in fact. And these Josephson junctions are in a circuit in a so-called transmon qubit configuration, where it's designed to have reduced sensitivity to charge noise. So you have two Josephson junction parallel with a large capacitor. And you can have anharmonicity, which means that the levels of the states are not evenly spaced. And so you can, if you have a large C, you can have selective qubit control. And then these qubits then can be built. This is a device consisting of 4 transmon qubits and 4 readout resistors. And of course, we have many more than that now. The Josephson junctions are kept at very low temperature. And the reason for that is that they use superconductivity. I mentioned Josephson junction. And so the low temperature that the qubits are kept at means that these are done in a cryostat. And that's that cylindrical device that is seen often with the qubits. And then when you have a number of qubits, as shown here, they connect together. And the microwave resonator, each qubit has a different frequency, and the microwave resonator is able to address and couple the qubits on the processor. So I've been talking about qubits, but of course the important thing is not just the number of qubits, but it's how good the qubits are. Because if you can't do a calculation because your qubits are losing their signal after a short period of time before you're able to finish your calculation, or before those qubits are reassigned to a different value, then of course you won't be able to get the answer that you need. And what's more, you have to be able to have a number of gates and to execute those gates without the signal being lost. So the question of how big a quantum computer one has, big meaning in big quotes, really has to do with quantum volume and the idea that the error rate and other aspects have as much importance as the number of qubits, and that you can increase the number of qubits, let's say from 50 to 100. But if your error rate decrease is not at all, your quantum volume increase is not. So you have to be able to increase the quantum volume. You have to be able to decrease the error rate. Let's say that you don't add any more qubits, but your error rate decreases by 10 times, then the quantum volume increases by a factor of 500. So the way to having enough qubits, and that those qubits have enough capability to do your calculation, that is the climb that we are on now. And as I'm going to describe, we are already in the so-called NISQ era, where although the qubits are not completely error-free, we're still able to do many calculations of great interest. We can also correct the errors. And so this is a paper that appeared in Nature last year that said that to be able to increase your accuracy, you actually have to do some calculations that have more noise, and then you extrapolate to the zero noise limit by doing calculations at different amounts of noise. And this is called noise amplification, or stretch. And this process can actually give a very good error reduction. And these error reduction results can be used, for example, in a chemistry calculation. So the IBM in 2017 did calculations of molecules where, like, let's say, lithium and hydrogen, and you can see the pinkish reddish line, and then the quantum computing dots, and they're not they're close but not quite on it. And then a year later or so, it's 10 times better, and the match is very good. And then this later paper came out, and we can see here that with the error correction, the match to calculations for all three little molecules are much improved. And I'll be talking about my own research in which we actually use the error to actually vastly improve the match to experiment. So the IBM Q experience. So quantum computing, of course, can be done in a variety of different modes and ways. And one way is the simulator. And one can do calculations on the simulator, which is a classical machine that simulates a quantum computer. And the advantage of that is that it has no error. The disadvantage is that it's automatically limited by the maximum size of quantum computer that can be made. I mean, not a classical computer that can be made to simulate a quantum computer. And so instead, I feel it's great to work actually on the hardware. And so I'm going to be describing some results and runs that we have done on the hardware. So running on the hardware, if you want to get started, there is the site to do it. And you can see a small picture of a composer, and you can see here what that composer looks like. So the composer is you can say how many qubits you want depending on which backend you're going to run in, and then take your gates from the choices and set up a small simulation there. If you want to do, of course, a much larger simulation on a larger number of qubits, what is done is, of course, a Python program that one usually writes, and then the Qiskit, then there are packages that one can download to the Python program that allow you to define qubits, define gates, and to submit jobs to the hardware. And these days we have much larger than 4 qubits, and we can begin thinking about running some interesting hardware experiments. So there's a whole Qiskit community and ecosystem. If you want to get started with Qiskit, there's a very good tutorial, and also reference tutorials on a large number of topics. Here you have, in the left of the 2 panels, we have an example of what the Python code looks like, and the documentation, and you have the OpenQASM specification, and you execute them on backends, and you have the IBM Q Experience project, and so this is it's all explained very well on the website. And what's more, after signing up, this is all open to the community. Some of the machines are to IBM clients, but many of them are open to the community, and you can use the websites and find out about quantum computing and run programs on the qubits. So there are different aspects to IBM quantum computing. There's Qiskit Terra, which is for the foundational for the software stack. Aqua, which algorithms, and then there's AIR, AER, which is simulating error corrections. So now I think I'm going to go to describing my research, and my research is in the area that I'm going to be describing is of the 3 promising areas here: chemistry, artificial intelligence, and financial services. The area that I'm going to be describing is an area in chemistry. And I'm going to go describe my research, and I'm going to show you how an interesting calculations can be done with, in fact, very few qubits. So here are my collaborators. And we're going to simulate noise in a so-called quantum beat system. In a quantum beat system, there are molecules, and these molecules have been zapped with radiation. And this radiation, they're floating in a liquid, and they get zapped. And then this radiation draws off an electron, and this electron leaving the molecule leaves the molecule with magnetism, a spin. And a number of these molecules in the solution can interact, and their spins can align and then anti-align. And what is found is that in these systems, there are singlet to triplet oscillations in a strong magnetic field, and that we can see that the singlet state, that is when they're anti-aligned, that population oscillates as a function of time. We thought, why don't we try to calculate that? So here are some examples of the radical pairs with spin. Now, you may remember my background is in physics, not in chemistry. I've taken chemistry courses, but what my interest in these molecules is not the details of all the chemical bonds, but just the fact that they have a spin on the part of the molecule that has had the electron removed. And we want to look at the coupling of these molecules in solution. So we've noticed that, of course, everybody has experimental data, has noise. And like, for example, I show right here, this is an example of the experimental data. And you can see, in fact, that the noise seems to increase. So what is this a plot of? This is a plot of this, the ratio of these two oscillations. And the x-axis is a function of time, and the y-axis is the size of the signal. And you can see the oscillations that start out at low times, and then there's a lot of noise at higher times. And so we thought, could we not only simulate these oscillations, but can we simulate the noise that we see in the experiment as well? And perhaps use the IBM, the quantum computer, to actually the noise in the quantum computer model the noise. So we tried three kinds of noise modeling. We tried, first of all, Qiskit Air. So we modeled this on the simulator, and Qiskit Air, the module, has several different kinds of noise that can be used to model. And we chose one that seemed to model the noise as well as we could. We did so-called Kraus operators that I won't go into too detail, and inherit qubit noise on the hardware. I'll be describing that. So first of all, before we do noise, we can just see, for small numbers of oscillations, can we see these oscillations between singlet and triplet? We can do a model with each qubit representing one of the two electron spins, but we can optimize this since we only need the singlet population. And here we're going to say the singlet state is the two spins opposite each other, and the triplet state is parallel. So with no noise, we run on the hardware, and we can see the image that you can see, that in fact there's very nice fidelity, and we can actually map. This is now, remember, the hardware, not the simulator. That the hardware is able to actually oscillate with the same, with a very good match for just the first few oscillations, at least, to the theory. And so we can see that even in this so-called NISQ era, with some error in the not perfect logical qubits yet, but with some noise, you can see, in fact, the amount of noise. The qubits these days have excellent fidelity, very good fidelity indeed, and you can see the match to the theory that we can get with them. Then we can say, well, past the first few oscillations, of course, the experiment has a lot of noise. And so the first step is we modeled this using the simulator. So we thought, let's put in some of these types of noise that Qiskit Air has in its module, various types of noise. We tried them all singly in pairs to see what makes the best fit. And we found only one type of noise matched the data, thermal noise acting on the RZ gate, acting on each qubit. In other words, T1 and T2 error. And addition, we added some hyperfine coupling by modifying air using a term which is quadratic in the time. And you can see that it gives a very good flavor for the error. Then we did the other molecule, and it is a larger molecule, and the circuit looks only a little bit more complicated. And now we can add, start to add noise to this. So this is the start of the theory with the experiment. And you can see, by the way, there's this first funny oscillation. And this first oscillation is there because there's short-term interactions with the solvent. And so we just, so in theory, the experiment should actually be going up there, but it doesn't because it interacts with the solvent. So now we're going to try to model the noise in two different ways, actually on the hardware. The first way to model noise on the hardware are so-called Kraus operators. Now, Kraus operators have been around for a while. They are a way of modeling noise, or so-called dissipation, because they allow the decomposition of non-unitary evolution. And into the components, you can model amplitude and phase relaxation of the qubit states. Kraus operators are a set of matrices, and they can actually quickly become very complex. But we are actually, for these molecules that we have, because we have T1 equal T2 for B equal to 0 and T1 much greater than T2 for large B, this simplifies the Kraus operators so that we can calculate them. And here are the circuits that we ran on the hardware. And then we have, and you can see, in fact, that the Kraus operators are accurate on the hardware, are accurate to incredible accuracy of 0.011%. And we note that the hardware accuracy is partly due to the good fidelity qubits and also due to the circuit optimization. And I mentioned that before. It is important that when we run in this NISQ era, that not only do you not try to have, a large number of qubits that you're all expecting to have equal fidelity. Some of them will have slightly different fidelity than others. The key thing is not to have too deep a circuit. And if you notice the circuit that I showed, I'll go back, only has a few gates. Yet this circuit is complicated enough to do Kraus operators. And it is certainly enough to be able to match the error in the and match the both the experiment and the theory quite well. Now we say, what if we can use the noise inherent in the quantum computer and use that noise to model the noise in the experiment? And so with some temperature corrections, we get an even smaller circuit. So that's one advantage of using the qubits. We don't have to explicitly simulate the dissipative channels. We get the dephasing almost for free. So we have a very small and simple circuit with the RZ of theta doing the oscillations and the rest of the circuit doing the dissipation. And here it is all together in one plot. And you can see the green is the Kraus, and it fits things extremely well, run on the hardware. And the red is the inherent on the hardware, just using the hardware noise. And it has a very good fit too. In fact, one might argue that the Kraus in particular fits the data arguably better than the classical, because the classical is the so-called theory is in fact an approximation. That the Kraus actually models the dissipation better than the approximate theory and fits the data arguably better. And the hardware noise is also does a very good job. So just to summarize, we've modeled the noise in a number of different ways, and I was hoping to give you a feeling for how one can use a quantum computer both to run a circuit, that is the oscillations themselves, and then also to actually use the noise or model the noise and get some very interesting results. So that's the end of my slides. So I'm going to, let's see, I stop sharing and get out of the slideshow, and then get out of my slides here and go back to the talk. So now I think I'm close to the end of my time, and I don't want to run over and make everybody else late. And so I thank you all for listening. And I think we're going to go back now to Denise, and I look forward to discussions. Bye-bye.